In this video, we'll take a look at making some connections with rational functions and their equations and look at a couple of applications. In the first example, we're told the intensity of sound varies inversely with the square of the distance from the source. And we're told a specific example, the intensity is 25 decibels at a distance of 30 meters. And we're asked in A to find an equation to relate distance and intensity. Now this first sentence, the intensity varies inversely with the square of the distance. So the intensity, and this is the symbol for is proportional to or varies with. And when it says inversely with the square of the distance, that means 1 over the distance squared. Now to write that as an equation, then there's some constant, I'll call it K, that the intensity is that constant divided by d squared. So that's how you write it as an equation. Now we need to find the constant to actually write the specific equation here. If we solve for K here, K would be the product of I and d squared. So K equals ID squared, just cross multiplying. And so to find the specific constant here, we would substitute the 25 in place of I and the 30 in place of the distance. And so 30 squared times 25 is 22,500. So if we substitute this K in place of the constant in our equation, then this is the equation. So the intensity is the constant 22,500 divided by the distance squared. Now in B, I'm going to solve B actually two different ways. One way is you can just use the equation. The distance has been reduced to 15 meters. So we're going to put 15 in place of D here. And so we're asked to find the intensity when the distance is 15. So 15 squared is 225, so we divide 225 into this number, we'll get 100. So the intensity would be 100 decibels. Now, another way you could solve that is you could say, well, the intensity was 25 at a distance of 30 meters. So you could say, well, okay, let's take our equation and we'll reduce the distance by a half. So 30 changed to 15. So the distance became a half the distance. Now if you square a half d squared, you get a half squared is a quarter, and of course d squared would be d squared. And when you divide by a fraction or a rational number, it's the same as multiplying by the reciprocal. So this is actually equivalent to the reciprocal of a quarter, which is 4 over 1, or 4, times 22,500 over d squared. Well, this is the original intensity of 25 decibels. So 25 times 4 should give you 100. So just a little different way to look at it. On the second page, we're told that the maximum time, and t is in minutes here, a diver can rise without stopping for decompression on the way up to the surface is defined by this equation. So t is the maximum time. T is a function of the depth of the dive. It's 525 over the depth minus 10. And so here's the what the graph looks like. And we're asked for the maximum time to be less than 25 minutes, under 25 minutes, how deep can the dive be? So if the maximum is less than 25 minutes, that means that this 525 over d minus 10 must be less than 25 minutes. So I'm substituting 25 in place of the t. And so it goes less than 25 minutes. That's why we have the less than symbol here. Now we're trying to solve for d. So the only place I have the variable d is in the denominator. It's a d minus 10 here. So what I would do is multiply both sides by d minus 10 so that those divide out. I'm trying to solve for d here. And so I now have 525 is less than 25 times d minus 10. Now I'm going to expand the 25 or distribute the 25 into the d minus 10. And I'm going to actually switch both sides at the same time because I like to have my variable on the left. So 25 times d is 25d. 25 times negative 10 is negative 250. Now this is the greater than sign. Notice the inequality opens up towards the side. This is the bigger side. So that's why if I put that on the left, I have to switch my inequality. And then 525 is on the other side. Now adding 250 to both sides, or bringing the 250 over, we would get 25d is greater than 775, and then we'll divide out the 25. So the depth would be greater than 31. So in order for the maximum time to be less than 25 minutes, the depth would have to be greater than 31 minutes. Now what that looks like on the graph is this. Here's 25 minutes right there. So notice it crosses the graph about right here. That's the 31 meters. So now time is on the vertical axis. This is one of the few graphs you'll see the time on the vertical axis. And so if there's the 25 minutes, so the question says for the maximum time to be less than 25, and so less than 25 means we're in this range right here, below the dotted purple line there. So the times are less than 25 minutes, and so the depth would have to be greater than 31 because we're down here. Of course, the further we go to the right here, the lower the depths get, or the deeper they get. Flipping over to example 3, and we're going to take a look at one example here and one on the next page as well. It says sketch a graph of each, explain what is special about each graph. So the first one is f of x is x squared minus 7x plus 12 over x minus 4. Now this numerator will factor. And to factor it, think of two numbers that add to negative 7 multiplied to 12, and that would be negative 3 and negative 4. So that factors into x minus 3 times x minus 4. Now notice that we have the same factor in the numerator and denominator. So those x minus 4's will divide out. And so this rational expression simplifies to just x minus 3. Now, these two expressions are equivalent. So this is equivalent to x minus 3, except there's one slight difference. Because I divided this x minus 4 factor out, I could not allow or permit x to equal 4 in this. Because if x was 4 in this factor that divided out, then both of these factors would have a value of 0. And so if they have a value of 0, then this function would be undefined. See, if I put 0 here, the denominator has a value of 0. If I put 0 here as well, the numerator actually ends up having a value of 0 as well. It's because of the x minus 4 factor. So these two things are equivalent, except x can't equal 4 here if this represents this simplified. So when I draw this line to represent this function, I'm not allowed to allow x to be 4. So what that means is there's actually a hole in this graph. So we draw this line. This is actually the equation of a line, except if this actually represents this simplified, then there's a hole in the graph where x is 4. So if I put 4 in place of x here, 4 minus 3 would be 1. So there's a hole on the graph at 4, 1. So at 4, 1, which would be right here, that was 4, negative 1. So 4, 1 would be right here. Otherwise, I just draw this graph as the normal y equals x minus 3. It has a y-intercept of negative 3, so it goes through the y-axis here, and would have a slope of 1 because there's a 1x here. So we would start here at negative 3 and go over 1, up 1, over 1, up 1. And so this is what the graph looks like. So that's the line f of x equals x minus 3. Again, there's the hole. If you actually were to take your graphing calculator and graph this, and as long as you graph it choosing the correct window size so it actually plots a point at where x is 4, you actually will see the hole in the graph. So this function is equivalent to x minus 3. So it simplifies to f of x equals x minus 3, except there would be a hole at the point 4, 1. Because this function actually cannot be defined, is not defined where x is 4. One last example on the final page here. And so we're going to graph this function here. And once again, the numerator and actually denominator both will factor here. And I'm not going to take the time to actually go through how the factoring works. That would be that's another lesson. But the numerator factors into 2x minus 5 times x plus 5, and the denominator into 2x plus 1 times x plus 5. So we have a common x plus 5 factor in the numerator and denominator, so they'll divide out. So this would simplify to 2x minus 5 over 2x plus 1. So this function is equivalent to 2x minus 5 over 2x plus 1. And of course, the x plus 5's factor out. So the value that would make each of those factors 0 is negative 5. So this is equivalent to this, except I cannot allow x to be negative 5. So at negative 5, this would be undefined, so there's actually going to be a hole in the graph when we graph it. See, this is a simpler version of this, and they're identical, except this graph actually doesn't exist at negative 5 because of those x plus 5 factors that divide it out. Now, to find where that hole actually is, and of course, this is the vertical asymptote. If we set the denominator to 0, or this factor 2x plus 1 here, it doesn't matter, we would get -1. So that's just a vertical asymptote. The -5 comes from these factors. It's where the hole is going to be. So I would substitute a -5 in place of x here, and actually there's my vertical asymptote. And I'll draw the horizontal as well. You can get the horizontal asymptote, it's y equals 1, or f of h of x equals 1, by taking the ratio of the dominant terms. 2x over 2x is 1, or 2x squared over 2x squared is 1. So that's where the 1 comes from. So if I put -5 in place of x here, 2 times -5 minus 5 over 2 times -5 plus 1. And that works out to -15 in the numerator and -9 in the denominator, and that simplifies to 5/3. So this would be the point -5 comma 5/3. So -5 5/3 would be about right here. So I know that that's a point in the graph, and I could take a look more at in more specific detail at the horizontal and vertical asymptotes, but if there's a hole right there, then, and I can investigate what happens to go to the left and of course around this vertical asymptote, then I'm pretty sure that the graph is going to go like that if the hole is actually here. I could, for example, to figure out what happens on the other side of the vertical asymptote, evaluate the function for a large value of x to see that it stays below the horizontal asymptote or stays above. So for example, I could, for example, put a large value in place of x here. So let's say 100. And actually, I'll do this one. So let's say I was going to evaluate h of 100, just to show what happens to the far right. So we would put 100 here in place of x. So we would do 2 times 100 minus 5 over 2 times 100 plus 1. So in the numerator, 2 times 100 is 200, minus 5 would be 195, over 2 times 100 would be 200, plus 1 is 201. So notice that that is a little bit less than 1. If we were to divide that, the numerator is a little bit smaller than the denominator, so that's a little bit less than 1. So that's how I would know that as we go out to the far right here, the graph is staying below the horizontal asymptote. I could also investigate what the y-intercept is in this function here. If I put 0 in place of x here and here, then h of 0, and of course I could do this in the original function too, 2 times 0 minus 5 over 2 times 0 plus 1, well, that's all 0. Those actually don't divide. I'm just crossing them out because they're 0. So we get -5 over 1, which of course is -5. So h of 0 is -5. So I know that the graph goes through the y axis right there at -5. And so those two things alone would be enough for me to know that the graph goes like this. So the original function simplifies, or is the same as h of x equals 2x minus 5 over 2x plus 1, except of course with a hole at -5 5/3. And so that's how we could graph this function. It simplifies this function except with this hole at -5 5/3. And that's the end of the lesson.